A cylindrical tank with a radius of 3 meters. Boy, that's a big tank, isn't it? Radius of the base is 3 meters. By the way, what do we mean by a cylindrical tank? We just mean a right circular cylinder. Like a can of food in the grocery store, only this is a huge cylindrical tank. The rate, okay. This tank is being filled with water at a rate of 4 meters cubed per minute. Notice that's a volume. That's the volume of water going in per minute. How fast is the height of the water increasing? So you realize as you pour water into this tank, the height's going to increase. How fast is the height going to increase? So write all the rates in the problem as derivatives. One rate is 4 meters cubed per minute. The units are huge in related rates problems. Meters cubed, that's a volume. This is derivative of volume with respect to time. Meters cubed is a volume. And then the only other rate is how fast is the height of the water increasing. So we need to find dH dt, where h is the height of the water, not the height of the cylindrical tank. We know the height of the cylindrical tank is constant, but we want to know the rate at which the height of the water is increasing. Okay, only 2 rates in this problem. Step 2, identify the dependent variables in the derivatives. Find an equation relating them. Okay, the dependent variables are V and H. So I need an equation that relates V and H. Volume and height of what? Well, it's a circular cylinder, really a right circular cylinder. The H is the height of the water. The R is the radius of the base. And the V is the volume of the water. Now, it's fine to go on and put R is 3 meters here, because that's not changing. This circular, right circular cylindrical tank, the radius isn't changing a bit. So usually in related rates problems, don't substitute values till the end. But that's something that's constant in the problem and not changing. Okay, the water forms a right circular cylinder, right? The shape of this water conforms to the shape of the cylinder. So we need a formula that relates V and H for a right circular cylinder. So Google volume of a right circular cylinder, and you will get volume is the area of the base, which is pi r squared, times the height. So in our case, the volume is pi times 3 meters squared times the height, or 9 pi times the height. Step 3. Differentiate both sides of this equation with respect to t. So dv dt equal derivative with respect to t of 9 pi h. So that's 9 pi, constant multiple rule, 9 pi comes out front. So this is our equation that relates those 2 rates. Now, what if we had said we had left the volume as pi r squared h and had not filled that 3 in for r. Well, if that's the case, dv dt would be derivative with respect to t of pi r squared h. The pi is a constant. Then for this r squared h, the derivative of that, that's a product, so I'd use product rule. So it's the first times the derivative of the second plus the second times the derivative of the first. So this would be dv dt equal pi times r squared dh dt plus h. Derivative with respect to t of r squared, I need chain rule. That's 2r dr dt. Again, derivative with respect to t of r squared. Derivative of the outside is 2r. The derivative of the inside is dr dt. Okay, so we would have had dv in this what if scenario, dv over dt equals pi r squared dh dt plus 2 hr dr dt. Okay, we'll get the answer for both these scenarios, the real one and the what if one. Okay, step 4, substitute values and solve for the unknown derivative. So for my dv dt equal 9 pi dh dt, my dv dt is 4 meters cubed per minute. And I want to know dh dt. So I just solve this equation for dh dt. So I get, and I need my units. This 9 really is 9 square meters. This 9 really is 9 square meters. It's 9 square meters. So dh dt equal 4/9 meters cubed, 4 over 9 pi rather. Meters cubed over meters squared is meters. Then I have per minute. Those units are right. A measure of height would be meters. Okay? That's my answer for dh dt. The height, of course, is increasing. The answer here is positive. Now, what if, here's my what if. What if I not substituted that 3 till the end? Watch this. I would have dv dt equal pi r squared dh dt plus 2hr dr dt. So let's substitute values. That's 4 meters cubed per minute. What's the radius? It's 3 meters. dh dt is what we want to know. The height we don't know. The radius is 3 meters. But what's dr dt? Well, it's the derivative with respect to t of 3 meters. That's a constant. So that's going to be 0. So this last term is just 0. So I get, because the 3 is a constant. So 4 meters cubed per minute equals pi times 9 square meters dH dt, again, plus 0. And look, I get the same thing. I get 4 over 9 pi meters per minute equal dH dt. It's just that in this what-if scenario, I had to do more work, right? But sometimes it's kind of hard to know when you can substitute a variable and when you can't, a value. So if you're hesitant to go on and substitute that value of the radius till the end, that's okay. We get the same value.